So we are going to talk about this thing here, rational zeros of polynomials. Okay, rational zeros of polynomials. And what this ultimately means, guys, is that we're going to be able to take and figure out if our polynomial crosses the x-axis, we're going to be able to find the places that it does that at if they're rational locations, meaning that they're written as a over b. So they're either integers or some fraction. Okay. Ultimately, all this does is looks at our x-axis, says if we're going to cross it, this technique will get us to be able to see where it crosses at all points, unless they have like radicals in them, like radical 3 or radical 2 or something like that, or if they have like pi or e or something like that. Does that make sense? Okay. So it'll give me all those locations where we potentially cross the x-axis as rational values. Okay. Now, to help us understand kind of the logic of the next theorem, I want to look at this slide here. We could prove the next theorem. It's not really that difficult to prove the next theorem. Okay. But it would take us maybe about 10, 12 minutes to do that. I don't think today that makes sense to do. Okay. I might put together a quick video and send that out to you. So if you're interested in that, you can watch that and benefit from that. I think doing proofs is a very, very good process for you, especially if you know that you're going to go on to a higher level of math at some point. You're going to get proof classes that are just solely proof work. Okay. So I think getting kind of a little bit of an understanding now of what that looks like is a good idea. But I'll put together a video and make that optional for you all. But what is going on here? Maybe we can look at a specific example. And why is this not a proof? Because this is only showing you for this one situation, right? Our proof would show this for all possible situations, all possible polynomials. But what it's saying, think about, we're kind of going to work and look at this in reverse form. If I have x minus 2 times x minus 3 times x plus 4 as my factored form of my polynomial, okay? If I were to go through and FOIL this, okay? Think about FOILing this. You would multiply those two things together. You would get a trinomial. But when you take last times last, you get 6, right? Okay? So then you would take that trinomial, whatever it is, and you multiply it by this binomial of x plus 4. And at some point, you're going to do last times last again, right? What's that quantity that you get when you do last times last again? You get 24, right? So what we're seeing here in this factored form, that p of x, is that the negative 2, the negative 3, and the 4 are all going to get multiplied together to give me 24. Okay? So if that's the way it works when I go from factored form to expanded form, when I reverse the rules, when I go from expanded form trying to get to factored form, hopefully that shows you that the only things that could go in the x minus 2, the x minus 3, and x plus 4 binomials are the factors of that 24. Does that make sense? Because that's what 2, 3, and 4 are. Now, they're not the only factors. We've got 1, we've got 2, we've got 3, we've got 4, we've got 6, we've got 12, and 24. Those are all, and 8 as well, right? Those are all, and 3. Okay, I think maybe I missed that one. But those are all factors of 24, correct? Now, they don't all show up there, but the ones that do show up there were all members of that group of factors. Does that make sense? Okay, so that's kind of where what we're going to talk about here kind of originates. Okay, is that if this thing is going to factor down to something like this, then the factors of this number here become very important to us. Okay, likewise, the factors of this number here become very important to us. Okay, because we could start the problem by factoring kind of a GCF, or I know you have a GCF, just say whatever that leading term is, factor that out, and that would then play a role in what these things turn into. Okay, and again, that explanation is a little bit easier to explain with the generic proof than maybe a specific. But this is what it's called. Okay, it's called the rational zeros theorem. Okay, sometimes you hear it called the rational root theorem. But it says if the polynomial p of x, which is then written as our generic polynomial, okay, is in descending order, has integer coefficients. That's key. Has to have integer coefficients. So then you're thinking, well, what happens if I have a coefficient like 1/2, 0.3, or something like that? This would not work for us, kind of in the manner in which this theorem is written. But we can change things slightly to make it work. Okay? This is going to be really nice for us in regards to pretty much every polynomial that we're going to encounter. Okay? Says the a sub n cannot be 0. A sub n was 0, then the leading term goes away. And then we just have kind of a depreciated polynomial, which is kind of silly. So a sub n cannot be 0. We had to add a coefficient for our first term. And a sub 0 cannot be 0, meaning that my constant has to show up. My constant has to be non-zero. Okay? And then people say, well, what happens then if you don't have some? Because I know there's polynomials like p of x is equal to like x cubed plus x squared plus 3x. And so I know there's polynomials that exist like that. So you're telling me that the rational zeros theorem would not work for that. Okay? What I'm telling you is that once you have to apply your rational root theorem, you cannot apply it if your a sub 0 is 0, right? But what do you see that can come out of every one of those terms in p of x right now? X. So now I have x squared plus 1x plus 3. Now, that's kind of the p of x that you would use the rational zeros theorem with. Does that make sense? Because that has a coefficient of 3, right? Or sorry, a constant of 3, a non-zero constant. So you can kind of pull that GCN. And that's really what we want to do every time anyways, before we even do any factoring, is recognize that there's a GCS. Factor that out. And then kind of attack with the rational zeros theorem if that's the necessity. But what this says is every single rational zero of p, every single place that your curve is going to cross the x-axis is going to be in the form of p over q, where p is the factors of the constant coefficient a sub 0. So that's the 24 that we saw on the last slide, right? So it would be the factors of that are plus or minus 1, 2, 3, 4, 6, 8, and 12, right? And 24. Okay? So our factors of p are our numerators, and those are the factors of the constant coefficient. Q then is the factors of the leading coefficient. And the last one is just plus or minus 1. But if it was 2, it would be plus or minus 1, plus or minus 2. If it was 4, it would be plus or minus 1, plus or minus 2, plus or minus 4. It would be all the factors of that leading coefficient. Okay? If I divide those, then every single one of our rational zeros will be of that form. Okay? So this is going to give us a possibility or a list of potential zeros. Okay? Now what stinks about this is that the bigger a sub 0 becomes, the bigger my constant becomes, usually the more factors it creates, the more factors it has. Okay? Think about the number 4, not many factors, right? 1, 2, and 4. Think about the number 24, there was a lot of factors to that. Okay? So the larger the constant is, the elongated this process becomes, or the more elongated this process becomes. But it's the same process all the time. Now the question is, well, what do we do? Well, how do we address this when maybe we don't have integer coefficients? Let's say I have p of x is equal to, I don't know, 0.2 x to the 4th plus 4.3 x cubed plus 4x squared minus 2x plus, I don't know, 0.6. All right, and our question is, what do we do with that? Because this violates that right there, right? That's that integer coefficient. 0.2, 4.3, and 0.6 are not integers. But we can do something pretty quickly here. What can I multiply everything by so that my decimals disappear? 10, right? Now I'm multiplying everything, so I'm multiplying both sides. And that would give me 2x to the 4th plus 43x cubed plus 40x squared minus 20x plus 6, right? Okay. Now, that 10 is important because it's 10px. I want to factor just p of x. So can I divide both sides by 10 again? Okay, now divided by 10 again like that would just get me back to what I started with, correct? So let's be intelligent about it. It's divided by 10, the same thing multiplied by 1/5. Okay, so we can transform this P of X into that P of X. And now, look at this polynomial inside here. That is of this form here, defined by our theorem, which says we have to have integer coefficients, right? Okay. So that's kind of basically it's looking at that, looking at a GCF, a useful GCF that would change every single one of our coefficients to a integer, and I like to do it that way. Okay? I think that's the best way for me to figure out what that GCF is. 1/10 would be what I factor out of everything. Take the 0.2, the 4.3, the 0.6 to make them integers. So even though this theorem says this only works with integer coefficients, we can manipulate a P of X to create integer coefficients. Okay? So we'll see one of those examples probably tomorrow. All right, so I want to do an example. Let's see here. We'll just jump straight to this. All right, so it's very similar, guys, to what it's actually at some point it's exactly the same what we did in question 13 and 14 at the beginning of class from last night's homework. I'm going to start with 2x cubed plus x squared minus 13x plus 6. Okay? And here's the thing. We do not have the ability. Factor by grouping doesn't work here. Any other technique that we've learned so far this year, there's not a GCF or anything like that, but none of our factoring techniques work. Okay? So what do we turn to? Well, if it's quadratic, we turn to the quadratic formula, right? This is cubic. There is a cubic formula, but if you did a quick Google search for the cubic formula, it's about 3 pages long just to use the formula, okay? It's ridiculously stupid, okay? But it exists. The thing that we turn to is the rational root theorem, or rational zero theorem we just talked about. So we have to set this up, okay? In our homework, question 13 and 14, they gave us these C values, right? Okay, this is how they came up with those. They said, we're going to look at that number right there, and we're going to identify some P values. P values are the factors of 6. So those are, and we're looking at plus or minus. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. We then look at that coefficient and its factors and then give me our cube. So plus or minus 1, plus or minus 2. Okay. Not too difficult yet. All right. As long as we stay organized, guys, this process is not hard. Okay. But what is difficult is staying organized, making sure that we know what we've tried, what we haven't tried, where we're at within the process, that kind of thing. The next thing, once you have your P and your Q's, you then, and this is one of the places that people get really kind of mixed up with, is because they don't systematically write our P over Q's. And what I mean by systematically is that I'm going to go take this P value, and I'm going to write it over every one of these Q's. So I'm going to go plus or minus 1 over this first Q of plus or minus 1. Then I'm going to take plus or minus 1 again and write it all over plus or minus 2. Does that kind of make sense? I put that P on top of both of these Q's. And then I go to the next P value and do the same thing. Now before I go on, I don't want to write this stuff out too much. If I have plus or minus 1 divided by plus or minus 1, I can have a positive divided by positive, which will give me a what? Positive 1, right? I can have negative divided by a negative, which would give me positive. Or I can have a negative divided by a positive or a positive divided by a negative, and that would give me just a negative. So what's the only way that you come out with a result here or a quotient? I can only have, even though top and bottom were both positive and negative, I can really only have plus 1 or negative 1 returned to me, right? Okay? So I'm not going to write plus or minus 1. I'm not going to write the plus or minus on all of these, okay, on top and bottom. But now I'm going to do that with 2. So 2 will be plus or minus 2 over 1, and then plus or minus 2 over 2, right? And then I'm going to go to the next one. So we'll go plus or minus 3 over 1, plus or minus 3 over 2. And then the last one would be plus or minus 6 over 1, plus or minus 6 over 2. Okay? Now, if you guys remember the fundamental counting theorem, or fundamental counting principle from Algebra 1 geometry, it says Susie has 3 pairs of shoes, 4 pairs of pants, 5 pairs of shirts. Pairs of shirts, that doesn't make sense. How many outfits can we make for her? We just multiply those numbers together, right? So if I have 4 factors of P and 2 factors of Q, and I want to find P over Q's, yeah, there's 8 things. Taking the 4 things here, multiplied by the 2 things there, right? So you see that right now we have 8 options, and actually because of plus or minus, it's actually 16 options for where we cross the x-axis. Okay, that's a pain in the butt. That's a lot of things. Okay. Now what we want to do is make sure that we go through and cancel out the ones that are redundant. It's 2 over 2, already stated right here. Yep, that's a redundant one. Okay. Is 6 over 2 the same thing as 3? Yeah. Okay. So it gets rid of basically 4 things that we have to try. Okay, because they're repeats. All right. So here's what we do. Those are our possible or potential zeros. Okay. We might go through and we might find out that none of those work. We might find out all 3 of them that do work. Does that make sense? Okay. Now, this is a cubic, so we know there should be 1 real 0. It does cross the x-axis. Okay. But if it was a quartic or something like that, maybe it never crossed the x-axis. All right. This is how we do it. Okay. We're going to do synthetic division. We're going to take our original polynomial, 2, 1, negative 13, and 6. In our homework last night, they gave us those C values, right? These are essentially our C values, but we don't know which ones work. Okay? So we're going to start by plugging in one of them here. I'll just go with positive 1. And then we go through our synthetic division. Okay? If I bring my 2 down, and I multiply by 1, so that's 2 here, get my 3, multiply by 3, gives me 3 here, gives me what, negative 10. Negative 10 gives me negative 4. Okay? Is that a 0? No. Okay? So 1 does not work. Now I try the next one. And you're going to hate me for this, but with a smart board or a whiteboard, it's actually a pretty easy process. Okay? For you guys, it's probably not all that easy. Okay? You probably have to rewrite the synthetic division again. Okay? Or if you're using pencil, my suggestion would be just to write real light when you're first doing this. You don't know which one's going to work. Write real light. And if it doesn't work, you can erase it pretty easily, right? Okay? If it does work, then you can kind of embolden it or whatever, and then go from there. Okay? But 1 does not work. Try negative 1. So bring my 2 down. Gives me negative 2. Add that. Gives me negative 1. Gives me 1. Negative 12. And I think some of you are seeing that that's not going to work. Gives me 18 as a remainder, right? Not a 0. So 1 and negative 1 did not work. Okay? I'll show you tomorrow. There's some rules. One's called a upper and lower bound theorem. One's called Descartes' rule of signs. Basically tells me when I look at my quotient, the way the signs kind of originate can help me decide how to choose some of my possible values here. So now we're going to try 1/2. Bring my 2 down. Multiply gives me 1. Add that together gives me 2. Multiply gives me 1. That gives me negative 12, right? Multiply 1/2 by negative 12 gives me negative 6. I got a 0, right? So what does that mean? It means x minus 1/2 is a factor. All right, everybody? Now, here's kind of the general process. We don't know if that factor has multiplicity of 1, 2, 3, 4, whatever. Okay? We know it can't be beyond 3 because of the degree of the polynomial. But we don't know the multiplicity thing. So even though x, or my c value, or whatever we will call it, was 1/2, I would have to try that again to see if I get a multiplicity of 2, if that ends up being a second factor. Does that make sense? And you have to do that every single time. So I would put a 1/2 here. It's kind of the general process. Bring my 2 down. Give me 1. Bring my 3 down. Obviously, then it's not going to work. So it's got a multiplicity of 1. Is that all right, everybody? Now, here's something you want to be able to look out, though. Because in this one, that really wasn't a necessity. Because if this was x cubed, what is this depreciated polynomial going to have right here? X squared. So right now, we know our p of x is actually x minus 1/2 because of this factor here. But then it's got the quadratic factor of 2x squared plus 2x minus 12. Is that factorable? Yeah, take a 2 out of everything. Gives me x squared plus x minus 6, right? And that's going to be 2 times now x minus 2x plus 3. And then also we have the x minus 1/2, right? And this is all multiplication, so I can rewrite them in any order. But that then provides us our factored version of p of x. Okay? Now that 2 that I took out can't just disappear, okay? Because it is applying a stretch to my function, right? But if you want to leave it out front, that's fine. I like to leave it out front. I like all my coefficients in these binomials to be 1x, okay? But if you want to multiply this out and say, well, it's 2x minus 1 right here, that's fine. If you want to put it in here, it's 2x minus 4, that's fine. Can I put it through all of them? No, if I put it through all of them, then I'd actually have a factor of 8 there, which I don't want, right? So if I want to multiply that 2 through, I can only pair it up with one of these 3 binomials, okay? I prefer to leave it out front. Is that okay with everybody? And now that we have it in that form, we know the zeros are 2, negative 3, 1/2. We can factor it. Or we already factor it. We can now graph it. We know our y-intercept is 6, right? It's a cubic. We know the end behavior. As x goes to positive infinity, y goes to the positive infinity, x goes to negative infinity, y goes to negative infinity. We have everything we need to graph that thing, right? Okay, and that's the reason we're doing this stuff. Okay. Tomorrow we'll talk about. Okay, so some of these guys we might not get a factor until that last plus or minus 6, and that'd be a lot of work. So tomorrow I'll show you some techniques that kind of simplify things.